Hello again, everyone. I'm back to do another little exploration. This time it's more of an experiment. I would like to tackle the concept of the shape of the Earth that we walk on and fly above sometimes. I'd like to take an approach that is personal calculation, how to verify something personally, if you can, rather than take the second level knowledge, which is getting it off of another entity, somebody else who did the calculations for you. And then that could be either an entity that wasn't very well informed, and it could also be from an entity that was informed. By and large, the approach here is to do something pragmatic to verify what shape the Earth is in. I'm going to use geometry for this, I'm going to use physics, and I'm going to use the concept of what calculus would do to help in the situation. Now, the main thing to start off with is the concept of our perception, before I get into the geometry and everything, and that is that we, by and large, don't have the Earth in our head. We only have our perception and then some kind of a form in our heads created out of what we have perceived, out of what's out there. And one of the brain areas that is involved in creating our perception of the surroundings are what are so-called grid cells. They're sort of like a triangular shape, if you will, like this. And then they quite literally line themselves up in our nervous system as a grid. Thus, they're called the grid cells. And what the brain does is it creates spatial recognition by applying the firings of these grid cells in comparison to what the real world is. And like any system, so do the grid cells have a capacity of how far our brain can understand a certain quantity. For example, how far something is or how many things there is of. Although that's more in the calculating zone. But by and large, there's firing of neurons to figure all this out. And humans are pretty good with understanding the distances of, say, within, 100 meters or up to a kilometer. And then once we start talking about 100,000 kilometer or 1 million kilometer or, 100 million kilometers, the brain reaches the capacity of being able to keep track of every single, meter in between or an inch in between. And rather what the brain does is that it, especially human brain, is takes the larger entity, makes it smaller, and then you end up with something like this, like a large sphere that we live on. And so as a result, what we have in our head is not what we even necessarily, for humans especially, what we observe directly around, but rather what we calculated in our heads that is going on. Okay? Now, as far as I'm concerned, we physically live and perceive a flat Earth, and have been ever since we evolved. Only until recently, when mathematics was invented or expressed itself through the human brain, did we start to make larger, expansive sort of style of knowledges, or like calculations in this case, that we could derive these kinds of conclusions. But by and large, everything around is flat. If you look around, and the reason why that is because, let's say, with a curvature of a surface that one lives, once you zoom in into one area that is by orders of magnitude, that's the thing, the difference between 1 and 1,000 and a million and then a billion are all orders of magnitude expansions. So once we go, say, consider the Earth to be round, and then we zoom in to a point where the distance between the curvature here that's left and the actual line that will be drawn becomes statistically insignificant. Statistically insignificant means, well, a few orders of magnitude. When something is 1/millionth of a something, that's why we don't, when you're trying to, smoothen a surface, the more you zoom in, the more you get to the atoms, right? So at some point it gets nullified. So when things are built in our world and around us everywhere, bridges and buildings, there's no need to adjust for the curvature of the Earth, because the localized world is quite literally flat. And this is the difference between what flat means in a smaller system versus a large system that could be actually would have a curvature. So everything for a person who walks in a small tribal setting in a forest, no matter how far that person walks, the Earth will always be flat. Things will be perceived as flat around. And from that angle, as far as our brain is concerned and how it evolved to understand the world, as far as it's concerned, and as far as whatever it is that it needs for its survival, it is completely good enough for it to consider and treat the world and the earth around as if it is just flat. And then, once you start creating crops, and then you want to observe why the sun moves in certain ways, and you want to start calculating, that is, yet again, higher order knowledge that is derived through thinking animals, right? Such as our species. Now, let's figure out the shape of the Earth. The actual shape of the Earth. After all, our brain creates a grid through the grid cells, the grid. And let's figure out what that grid is as far as the Earth that we walk on is concerned. Let's say we have a map that is on some surface. Right now it's a flat surface. And I'll take a few spots. I'll take Santiago here, then I'll take Vancouver, okay? Then I'll take London, and then I'll take Sydney here, and then I'll take Tokyo right here. If we are to honor the physics of our world, if you were to say sit in a car and drive all the way from Vancouver to Santiago, and you personally kept track of each kilometer on it, and agreed that there's no bending of space in between, as in the physics remains very consistent no matter where we move along the entire line between, say, Vancouver and Santiago. It would shape a specific length, okay? And I'm going to calculate the direct lengths. So I would draw a line here, then I would add another town, and I would draw a line between each of the towns, okay? Then I would add another spot, right? And connect all the three. Tokyo and these ones are pretty similar, as you'll see here, right? So they're pretty much on the same line here. On a flat surface, on the map as drawn as this, okay? And then we take the last one, and we'll connect all of them, okay? And what this creates is a bit of a grid. And this grid, like a wire system, will keep and constantly build on creating the shape of the surface that these dots are chosen out of. So for example, if I chose a dot that's higher up here, right? Like if I went up here somewhere and I made a line from there to there, all of a sudden that line would be longer than the one right underneath, right? And if it goes higher, then all of a sudden this line would be, and it'll start going to three-dimensional surface. Basically, if something is flat. If something is slightly oval, it will always connect on that level. Now, direct connections would actually not be directly on the surface yet. But the more spots you add, if we continued to add spot after spot and connect every other spot with every other spot, of course, this exponentially goes high. So it's a lot of work. That is what calculus really does. You take the variable of, the next city or town that you'll choose, or a spot on Earth that you'll choose, and then you push that to infinity. As in, we'll choose every single spot and build it's going to like pumping up a balloon. It slowly gets itself into the shape that it needs to go. All right, here we go. I had to do a little bit of prep work. What I've done is for each town or city around the world, I've assigned different colors. And for each, I will be connecting physically little wires like this, okay? That will correspond to the distances between the cities, okay? Now, Santiago to Vancouver is one good example, which is about 10,550 kilometers. Now, this figure is something that one can personally verify. You could walk to Santiago from Vancouver if you really wanted to, or drive, or take a long time depending on mode of transport. But it is something not only that you can verify yourself, but it's also something that is getting verified all the time. So the more time you verify something, the more precise the measurement can get. And these numbers don't change. And these are the direct lines from Santiago to Vancouver. So of course, if you walked, it would be probably much longer because you'll be doing some kind of a non-straight path to get there, okay? Which is technically what a curvature of any spherical-like surface would do to the length. If it is just a flat surface, it would be the shortest distance. But the moment you start adding any kind of curvatures, the distance changes. So I've got little erasers that I've turned into cities. And this is where, again, the more cities you would add, the more each distance from each city would define the surface that you would be walking on. Okay, we're going to connect, therefore, Santiago to Vancouver first here. And for every 10,000 kilometers, I'll truncate that to 10, which is 10 centimeters. So Santiago to Vancouver will be about 10 centimeters long, which is 1 decimeter. So I'm going to go from Vancouver, and I'll try to do it as much as I can into the middle, to Santiago. Okay, that's the first one. The second one is from Santiago to London, which is about 12 centimeters, let's call it, okay? And that's going to be from Santiago, orange, and we're going to be approximating all of this. If we lose a few millimeters here and there, at the worst case scenario, if everything's flat, we'll get somewhat of a horizontal but uneven terrain. And in case of any kind of a sphere that we might end up, it might not be the perfect sphere, it might be a bit lopsided. Sort of kind of like when you sit on a football or soccer ball and it bends, right? And then from Vancouver to London, we've got 8 centimeters, okay? Seems this one. So currently, with this setup, we've got, with only 3 lines, it's impossible to know whether it's spherical or not, right? It could be a plane, or maybe it could be one of those oval things, or it could be within some kind of a spherical. But we can't know. It's only 3 points. So we're going to continue. Now, we're going to add Tokyo. All right? So let's connect the next one over, which Santiago to Tokyo is 17,000 kilometers, 17 centimeters. So let's just keep this somewhat consistent. So from here to here, I'm just going to put it on the side, and if it evens out, here we go. So from here to Tokyo. All right. Now, we still don't know whether this is, Tokyo could be on a plane. Hang on, let me make sure. Tokyo would be, it could be on a plane. It could be over here. It could be really anywhere. So we've done this one, we've done this one, we've done this one, and we have done Vancouver to London, yeah? And now we're going to do Vancouver to Tokyo, which is, it says 7 here. I don't know why I added up to 10 from there. That's a mistake. So let's say that's 8. In which case, I have an 8. Tokyo to Vancouver. And notice, even in this case, when we have, it could technically still, it could technically still be in a plane. It's once you come to the pyramid structure, where you have 4 dots that are all connected amongst each other, that's when the real definition of whether the elements are in a plane or not will come true. So everything will be dependent at this point from the distance between London to Tokyo. So I could expect it, for example, if it was in a plane, I could expect it to be short like this, and it all of a sudden starts tying into a plane. Or it could be maybe on the other side, like this, right? On the other side, also a plane. Or maybe it'll connect in some other way. Let's see, maybe if it connected like this, so instead of being a plane, hang on, instead of being a plane, if it was like this, then it might be not fully spherical, just an angle of a sphere shape, right? Let's do it. London to Tokyo is 10 centimeters. And London to Tokyo. Here we go. It's the moment of truth. See what will happen. All right, so here we are. It is most definitely not on flat surface, right? One would expect that the more flattened the surface is, the more Vancouver in this case would sink down into an area that is pretty flat-ish, right? But for me, this kind of a triangle suggests that they're on the opposite sides of something that is in the middle of, which is the Earth itself. But let's see. Let's put another 4 connections and see what kind of a shape we're going to end up with. Here we go. Santiago to Sydney is like this. And again, we need to connect the other ones to see where this one fits, right? Vancouver to Sydney is 10 centimeters. Next one, we've got London to Sydney. Entire 17. Look how long that is. This is going to stretch things out. It's like inflating a ball. Because the more, if it was flat-like, the surface, most of the distances between all of these setas would remain less than this initial 17 that we had. But now we have another 17. London to Sydney. So from here to here. Now, I can either run it around like this, because it's obviously not flat. It's going to be some spherical thing. It's either going to be from here to here, or I can patch it from the other side. I'm going to try for this for now, just to not complicate, and see what the other connections do or bring. Okay? That's what we have so far. It's the last one, in fact. Sydney to Tokyo is 8 centimeters. So here we go. Sydney, right here, to Tokyo. Check it out. Let me step back a bit further. Okay, see that? This cannot be on a non-spherical surface. You can call it an earth an egg shape if you want, because after all, I think it is technically not a complete sphere as measured. But this thing is becoming a sphere. And the way physics, mathematics, geometry, whatever you want to call it in this case, the more dots you add, the more the whole thing will be shaped into whatever the real shape is, because the distances cannot change. They are firm as firm can be. And to me, this is a way that I like to test whether I want to pursue looking into something further or not. Because everything here I can do with my own body and with my own eyes and with my own calculations to see whether something checks out. And the reason why to conclude this whole thing, the reason why we have to do this rather than just look outside is because to actually be honest to the argument, and that is that in reality, the Earth is flat around us everywhere, all the time. If you started walking across the Earth today on your own, you would always be on a flat surface all the time, because our existence is in an emergent system that is of orders of magnitude smaller than the system that the planetary objects exist and shape themselves. So their curvatures to us are so large that the error that we have to truncate is just like here. I was cutting off some millimeters off and shaving off and still allowing those kinds of differences in the slope or angle as we walk are in the millionth probably of a millimeter. And you can calculate this mathematically as well. That's why geometry and mathematics are simple tools to determine what is going on around us without necessarily even having to go outside into the space and see whether we see a round globe or not. Basically, that flatness is really our limit in perception, because we can't see that far. And I'll give it the fact that ships go down is one of those examples where eyesight allows for very large distances. And the ability to, especially with the invention of, technology such as binoculars and telescopes, now we have enhanced our ability to experience and see what's up there. The global curvature of the Earth is, for us, statistically insignificant. And I would say that a person who thinks that the Earth is flat, yet follows the round globe navigational maps, is technically not being honest with the fact that they're not using their own maps. A person who truly believes in the concept of an Earth being flat would start making their own maps and then claim that a city should be somewhere else where it's not, and quickly realize that it doesn't work. Our eyes and our immediate senses, when we look around, really see a flat Earth around. The Earth is flat around us. And we have biologically and evolutionarily been programmed to exist and function within the concept of things around us, at least when it comes to the Earth we walk on, is just simply flat with a bunch of mountains around. But bottom line for me, the maps of navigation, in this case, win the argument, because they really answer to us what the shape of the surface we're walking on is. And there's no running from that. That alone for me is enough to not give any more time or energy into the flat Earth models or not. For me, I just step away from something like that. And this is my testimony. So hopefully this was helpful, and good luck to you all out there. See you in the next video. Here we go. I happen to have a little globe of the Earth, and I've marked down Vancouver, London, there's Tokyo. Here we've got Sydney and Santiago in South America. And as you can see, we've got, just like there's a Vancouver here, we've got V for Vancouver. That's L, which is just like the green one. And this here is Tokyo. So these three are like that. And notice how underneath, right there, it's starting to pan out. There's our orange underneath here, which is Santiago. And right at the bottom, we've got Santiago, and the white one, which is Sydney, is right here. So this bubble is actually starting to resemble the globe Earth very nicely.